I've never flown a glider which then turns into a rocket ship, then turns into an exo-atmospheric vehicle, then folds itself by 60 degrees, re-enters the atmosphere, and then becomes a glider again. That's a phenomenal vehicle. The flight control system needs to be equally as phenomenal to accommodate all of that. My name is Andy Edgell. I'm a test pilot with Virgin Galactic. Working at Virgin Galactic as a pilot, I mean, it's a dream job. It's not just about flying. We're very much involved in the design and the engineering work that goes into the vehicle.
I'm David Clyde, Tech Fellow of Flight Controls at Virgin Galactic. I have 40 years of experience in flight controls, working with the DoD, NASA, FAA. That helped me bring that expertise to Virgin Galactic to work with a team of great engineers to make a great system. In our new Delta spaceship, everything is fly-by-wire, so we can tailor the software for the phase of flight so that we maximize the performance of the spaceship while minimizing pilot workload.
A fly-by-wire flight control system is the side stick connected to computers, and then those are connected through cables to electromechanical actuators which drive the surfaces. It's akin to any modern fighter jet or any commercial airliner that is being designed as well. The flight control system is almost entirely designed and it's ready to be put into the spaceship.
Our fly-by-wire system consists of 4 key components: the active side sticks, the central computer, the actuators, and the software.
The side stick is an active side stick. It's extraordinary. The active aspect allows us to design it for the specific phase of flight. The rocket boost, for example, you're immediately going to be thrown into the back of your seat at approximately 4 times the force of gravity. The pilots who are hand flying this vehicle during this phase are connected to the side stick, which are then connected to the control surfaces. We've designed a flight control system that doesn't actually require large magnitude of inputs. It operates and it thinks faster than I can, and I will fully acknowledge that. It's an instantaneous logic gate. It interprets where it is in its phase of flight, whether it's on the hooks under the carrier ship, whether it's now just been released, whether we're about to fire the rocket motor or we are firing the rocket motor, or whether we've completed that phase of flight. And so the flight control computer can make instantaneous changes to the way the side stick feels or to the way that the control surfaces are allowed to move based on exactly where it is in that phase of flight.
Our flight control computers are built in-house, designed by our team here at Virgin Galactic. It is the brains. That's why the avionics team refers to it as the central computer. And we have built in a triple redundant system so that each computer is backing up the other.
We have 6 electromechanical actuators on our vehicle, and they power the rudders, the elevons, and the stabs. They are our mechanical leverage. So a small input on the side stick is then translated through the actuators to move a surface against a thick, fast-flowing atmosphere.
All of our actuators receive current, and that current moves motors. The motors move gears, which the gears move the ball screw, and the ball screw moves the control surface. The stabilizer actuators have been to space 12 times. They're tried and true, and we are working to make them operate better with our new controllers, and they are now in acceptance testing, and we are also testing them on the test stand, including in the fly-by-wire bench behind me. So just this past week, we've hooked up our for-flight side stick, maneuvered that side stick with a trim control that went through the central computer to our actuator controller, to the stabilizer actuator, and made that actuator move for the first time, and there was much rejoicing. The secret sauce is the software. We have a release date of our software, and that is being tested regularly in our simulator. It's gone through a year of testing so far with our pilots. Each time we go into the sim for a different simulator entry, looking at all the different scenarios, we build upon that to the next test, to the next test, to the next test.
The role of the simulator, our piloted sim, it allows us to de-risk and expedite the flight test campaign. It is allowing us to design the interface between the stick and the rest of the vehicle. And that's really important because when we go into flight test, all we want to do is verify that what we did in the sim months before works for us.
And one of the things we did to reduce risk was the flying at Calspan. And so we were able to take our side stick characteristics and our model of our spaceship and put it on board their in-flight simulator and test a bunch of landing configurations, variety of side stick characteristics, variety of flight control characteristics to home in on what would be best for our spaceship. It was a wonderful risk-reducing event. We did 85 different approaches with 4 different pilots over 6 different flights and got a great set of data.
The flight test phase will be absolutely fascinating, and that's where you truly will reap the rewards of all of the hard work with the pilots and the engineers over the last few years. All of the pilots are engineering test pilots. This is what we do. We design a suborbital spaceship. It is the second best job in the world. The best job in the world I get when we actually fly this vehicle to space. It's been a huge amount of fun, but I cannot wait to fly it.
That's how we do flight controls. This is how we build spaceships.